Waarde genodigden, beste prominenten, dear invitees, dear prominents, dear Harvey. It's a pleasure for me to introduce you for your first talk today. Let me just give a very short survey of the achievements of Professor Friedman. Professor Friedman is a man of distinction. Now you can ask, what type of distinctions? Voila. I will just mention a few of these achievements. He is well known for being a very young professor at Stanford. At the age of 18, he got the job of an assistant professor. Before, he got his PhD at MIT. And 2 years later, he got a permanent position in Stanford too. In 1984, he got the Ellen T. Waterman Award, which is a very special award. It is going to the best scientists in the age of below 35 in the United States. It also comes with a reasonable amount of money. He was mentioned among the top 100 scientists in the US in the Science Digest in 1984. He got a Guggenheim Fellowship in 1987. And at his home university, Ohio State University, he got the title of Distinguished University Professor in 1987. So the program of today, I hope, is more or less known to everybody here. I will not recall it, but I will give some hints about the program for tomorrow. So Professor Friedman will start at 10 o'clock in Saal Rektor Vermeulen with 2 talks about his recent achievements in mathematical logic. After lunch, there will be 4 short talks given by the members of our department about certain facets of Harvey's work. And after 3 p.m., there will be 4 scientific talks by eminent international speakers, which are Albert Visser from Utrecht University, Ulrich Kohlenbach, University of Darmstadt, Matthias Barz, Universität Wien, University of Vienna, and Ali Enniat from the University of Gothenburg in Sweden. Around 6 p.m. there will be a second piano concert of Harvey Friedman. Today there will be the first one, also around that time. And after 7 o'clock there will be a reception. Today there will also be a reception. Yeah, thank you very much. And now I give the word to Professor Friedman.
Logic is an interdisciplinary subject, and I want to talk to you about some interdisciplinary events.
No, it's better.
Hello? I think that's better, okay. All right. Maybe I should talk about the technology of this, but I shouldn't because I don't know anything about it. But anyways, so logic, interdisciplinary adventures in mathematics, philosophy, computer science and theology. So the lesson from this is logic is everywhere, and now I can sit down. No, I think I should continue, right? Okay, I will continue. Or maybe I should go over there and play the piano. No, that's later, isn't it? Yes. Okay. All right, so logic as the science of reasoning. This is the classical role of logic as a science of reasoning, and we have a relatively deep understanding of at least some key aspects of mathematical reasoning, although logic in its broadest sense applies to reasoning outside mathematics as well. And logic, the modern view of logic, it starts with the logical connectives. The logical connectives support general reasoning that goes back to the great ancient philosopher Aristotle. And there are 5 standard logical connectives: not, and, or, if then, and if and only if. So if you say, for instance, it is warm today, and then you can say it is not the case that it is warm today, although that does sound a little bit pedantic, a little bit formal. Sometimes it's abbreviated, would be abbreviated by it's not warm today. And you're familiar with and. It's warm today and it's warm tomorrow. So that has and connecting, it is warm today and it is warm tomorrow. So these are called connectives, and or, and if then, and if and only if. And now, let's talk about a simple little piece of logical reasoning. We assume if Fred lives in Chicago, we make now 3 assumptions. I'm going to make 3 assumptions, and we're going to have one conclusion. The conclusion is Fred lives in a big city. So the first premise or assumption is that Fred lives in Chicago or Fred lives in New York. The second one is if Fred lives in Chicago, then Fred lives in a big city. The third one is if Fred lives in New York, then Fred lives in a big city. And then you can conclude that Fred lives in a big city. Now, if you just think about that, if you don't see that immediately, if you just think about that a little bit, you'll finally, inside of you, something will say, oh, I see, of course, that's obvious. Right? Because you can feel why this is true. Now, what logic does is develop a science of this kind of reasoning and give explicit criteria for when something like this is legitimate. Now, in this particular case, we all see that this is legitimate, but logic has the ability to turn this into a scientific subject. And this is called valid inference. So in this very limited context, we can mathematically define what we mean by a valid inference, and we can determine whether such an inference is valid by a method called truth tables. And I think some of you probably have seen this or heard about this, about truth tables. But I'm not going to go into this in detail because I have too much, as usual, too much material to cover. But nevertheless, truth tables. And in these days, you can type truth tables in Google, and you can get more information about truth tables than you'll ever want to know. Now, logic has to be more powerful than this in order to deal with more general, sophisticated reasoning, particularly the reasoning that goes on in mathematics and mathematical subjects. You can't simply be dealing with the connectives. As many as there are 5 connectives. You need some more firepower. You need some more firepower to be able to handle reasoning in mathematics and in many other contexts. And the main ingredient that's missing so far is what's called the quantifiers. These are called the quantifiers, and there are two quantifiers that are normally considered. The most commonly considered. These are the for all quantifier and the exist quantifier. There exists. So somebody might say, everybody is beautiful. Or they might say much more meekly, somebody is beautiful. See the difference between the two. Everybody's beautiful and somebody's beautiful. The first one is a for all statement, and the second one is an existential or exist statement. Okay, so Aristotelian logic makes very limited use of for all, so-called Aristotelian syllogisms. But it took another 2,200 years to incorporate the 5 logical connectives and both quantifiers, for all and exist, into a science. So incorporating the 5 connectives and the 2 quantifiers into a science was a subtle step historically, even though it's taught in basic logic now. It's one of these things which is the usual thing that in retrospect it looks obvious, and in the middle of the 2,200 years it didn't. All right, so this is a typical situation, and this structure is called predicate calculus. There's a grammar for this. So you can think of predicate calculus as what is often called a formal language, meaning it's like English, Spanish, French, and German, except, of course, totally different. But it's like those languages, except that it's very constrained and very formal and very specific. I think that, however, these natural languages have more scope. That's meant to be a joke, of course. They have more scope, but this has more exactness. All right, so there's a grammar for this, resulting in a formal language called predicate calculus, and I won't present this grammar, but I'll present a group of familiar examples. And from the examples, you can sort of imagine what this thing would be, and then you can go look it up and see the science of it. It's a very specific scientific mathematical development, incorporated in textbooks and so forth. So here's some examples of statements in predicate calculus with specific references to specific ideas. Okay, so these are essentially complete sentences, and then we'll talk about their structure in the next slide. Everybody loves everybody. Somebody loves somebody. Everybody loves somebody. Somebody loves everybody. Everybody's loved by everybody. Excuse me. Somebody is loved by somebody. Everybody is loved by somebody, and somebody is loved by everybody. And these are all the things you can. Obviously, these are all the things you can say with a certain pattern, where I'm using exists and for all. And the relationship X loves Y. The relationship one thing loves another thing. Now, we can, of course, debate and discuss the truth, which statements are true and which are false. And this might be an opinion. It might be a matter of opinion. But there are common views that the first is false, for example. The second, is arguably true. I mean, maybe one of you loves, the second is certainly true, or almost certainly true. What about the third? Everybody loves somebody. Well, that's probably false. People get into negative moods, right? And then somebody loves everybody. That was the one I was thinking about before. Somebody loves everybody. Well, that's probably true. I mean, maybe some of you love absolutely everybody. And then we know that you would know that this was true. Everybody is loved by everybody. Well, this I know personally is not true. Okay, for sure. Somebody is loved by somebody. Well, I think I know that. I certainly know that that's true. Okay. Everybody is loved by somebody. Well, that's dubious. That's probably false. And somebody is loved by everybody. Well, maybe so. I mean, it depends. That might be tricky, because there's going to be some holdouts, who don't love, I won't even mention whom. It's not me, but don't love this, this particular candidate for being loved by everybody. So there may be some holdouts. So that's probably false. Okay, but logic doesn't really care about whether these are true or false. Logic only cares about the relationships between these various statements. That's the point of the science of logic. So now here's some ways of expressing these things. Everybody loves everybody is expressed in predicate calculus by the upside down A means for all, and the backwards E means there exists. So the everybody loves everybody statement is for every X and for every Y, X loves Y. And so you get good at a course in logic. Take an English phrase like this and write it in logical notation, or take a logical notation like this and write it out in English. You get good at that, or you leave the course, or get a flunk the course, or whatever. Andreas can tell you about this, right? So, and then somebody loves somebody. There is an X and there is a Y, says X loves Y. Okay, and so forth. Now, look at 1 and 5. And also think about it. Now, 1 and 5 are not exactly written the same way. 5 is for every X, for every Y, L, Y, X. And 1 is for every X and for every Y, L, X, Y. So it's subtly different. But you can, if you think it through, you can see that 1 and 5 are saying the same thing. You think about it, are saying the same thing. And also 2 and 6 are saying the same thing. But 1 and 2 are not saying the same thing, and 5 and 6 are not saying the same thing, and so forth. I mean, I'm not spelling out all the relationships. Just wait for the next slide. There'll be some more relationships. And what logic can do for you in this situation is create a clear science of what you mean by 2 of these things say the same thing, or one is stronger than the other, or 2 statements are not the same thing at all. All of that is subject to a scientific test, and that's what logic does for you. It turns this all into an exact, that's the right phrase I want, an exact science. So it turns out that it can be shown by the methods of logic that 1, 2, 3, 4, 7, 8, so I've left out 5 and 6 in these earlier numbered things, are all logically inequivalent. So if you take 1, 2, 3, 4, 5, 7, 8, 1, 2, 3, 4, 7, 8, you take any 2 different ones that you can show that the 2 of them say different things, have different meaning, are logically inequivalent. And there's a method for actually establishing that and so forth. Okay. And in general, logical equivalence means under any interpretation of the concepts involved, the statements are both true or both false. So 2 statements are considered logically equivalent if under any interpretation of the concepts involved. Remember, logic doesn't care what you're really saying. It only cares about the structure of what you're saying. Under any interpretation of the concepts involved, the statements are both true or both false. And the modern treatment of logical equivalence is credited to Alfred Tarski in 2 papers, 1933 and 36. Not Aristotle 2,200 years earlier. This took a while to understand. Now, logical implications. One statement logically implies another if, in any interpretation of the concept involved, if the first statement comes out true, then the second statement comes out true. Now, notice I said, under any interpretation of the concepts involved, if the first statement comes out true, the second one comes out true. There may be many interpretations, different interpretations of the concepts involved, some of which make the first one true and some of them make the first one false, and the same thing for the second one. But the logical implication just means this, once again, every interpretation of the concepts involved, that make the first statement true also make the second statement true. And this is a picture of all of the implications that hold between, in this sense, between the various 8 statements. So 1 and 5 both imply 4 and 8, and 4 implies 7, and 8 implies 3, and both of those imply 2 and 6. Okay. By the way, you could read off from this that 1 and 5 also imply 2 and 6, because you can chain down. In other words, if A implies B and B implies C, then A implies C. So-called transitive law. All right. An inference in predicate calculus is considered valid if under any interpretation, if all of the premises are true, then the conclusion is also true. So an inference in predicate calculus is considered valid if under any interpretation, if all of the premises are true, then the conclusion is true. And we have a great theorem by a great person, Kurt Gödel, 1930. Every valid inference in predicate calculus can be backed up by a proof using only a fixed finite set of basic axioms and rules of inference. So this concept of logical implication can be pinned down by a system of finely many basic axioms and rules of inference. This is not at all clear, but it is true. Okay. However, Alonzo Church, 1936, addressed the following question. Is there a method by which you could tell whether one group of statements implies another statement? In other words, can you tell whether or not a single sentence implies another one, logically implies another one, or more generally, can you tell whether a finite group of sentences logically imply another one? Can you tell this by an algorithm? Is there a magic algorithm to say, yes, this follows from these? And the answer is no. There is no general method for doing this. And that's a theorem, but that theorem requires you to know what a general method or algorithm is. In other words, this is not a matter of nobody has found an algorithm for doing this. That's not what this says. It says there's none at all that exists. And in order for you to do that, you need to be able to turn into a science the general notion of algorithm. The general notion of algorithm has been turned into a science starting with Alan Turing. Okay. So we have this result. And now I want to talk to you about some positive things. So this is all, this thing is negative. If you notice, you see that in the right corner, I have here a face, right? You don't need to have a very fancy face to know that this is negative, right? This is an unhappy face, right? Okay, so, but now I want to talk about some happiness. So let's get happy. Some successes. And these successes I'm about to talk about have been applied in computer situations of various kinds, including robotics and various other situations. Artificial intelligence of various kinds. Okay, so let's talk about the integers. The integers are the whole numbers, including 0 and the negative and positive numbers. That's what the integers are. And we can add and subtract integers. At least I used to be able to do that. Now I rely on my calculator. But I don't know if my calculator really understands what it's doing. That'll take us into a different realm. But that's a different kind of talk. Let's go back to this. Okay, so I can add and subtract, or at least used to be able to, integers. And I can compare integers. I could even do that by these standard 6 comparators. You know, less than or equal, greater, equals and not equals. These are the standard comparators. And here are some examples of statements that you can make, and in predicate calculus, about integers with these concepts of addition, subtraction, and comparison. For example, you can say, for all integers x, there is an integer y, such that x is smaller than y plus y. Now, for those mathematical people in the audience, they clearly see that this is true. Okay, and for all integers x, there is an integer y, such that x equals y plus y. Well, I'll leave you with some suspense. Okay, and then we have something a little bit fancier. If I have two integers x and y, and if x is less than y, then I can fit z in between them. In other words, then I can fit z in between, meaning x is less than z, and z is less than y. So for each integers x and y, if x is less than y, then there is an integer z such that x is less than z and z is less than y. Okay. Now the first is true, whereas the second and third are false. Okay, and you can easily see this. The second one has a counterexample because of 1. 1 is not the sum of y plus y, because it would have to be a half. 1 equals a half plus a half, and a half is not an integer. So there's a sort of an argument. And the second one is also false. How do you fit an integer between 2 and 3? You can't. So that's a counterexample. So now I'm using, manipulations here that a for all statement can be refuted by coming up with so-called counterexample and so forth and so on. So I'm doing things that are second nature to people who are mathematically oriented. Other people might say, well, what is he talking about? So don't worry about it. This talk is meant to just paint an impressionistic picture of how logic looks. Okay, we don't need to. Now, for those mathematical people, you obviously better understand this right now. Okay, all right. So now we have a smiley face. There is a general method for determining whether a sentence in the predicate calculus, based on the integers less than plus and minus and the comparators, there is an algorithm for determining whether a sentence in predicate calculus based on these is true. Now remember the sad face of Alonzo Church about there's no general method for determining whether a sentence in predicate calculus is valid. If you remember that one, this is different. There is a general method for determining whether a sentence in predicate calculus based on the integers plus minus and the comparators is true. This is true, and this is actually useful and implemented. Now let's go to fractions. I used to even be smart enough to handle fractions. 3/4 minus 10/3, and 0 divided by 1, by the way, is actually equal to 0, as you might know. And we can add fractions, and we can subtract fractions, and we can compare fractions. And now I just simply ask the same thing. Actually, I consider the same sentences. So for every rational x, for all rationals x, there is a rational y such that x is less than y plus y. And that's true for the same reason. Now, what about the second one? For all rationals x, there is a rational y such that x equals y plus y. And if you think about it, what this really says, it really says that I can divide any rational by half, by 2. I can take half of any rational, and it's still a rational. And that's clearly true, right? You just double the denominator. And then this third one is also clearly true. It says that given any two rationals, if the first one is smaller than the second one, I can fit one in between. And for those of you who remember a little bit of math, you can take the average of the two. So if you have, for instance, x, and if x is less than y, then in between x and y is x plus y over 2, the average of the two. Okay, so you either are slightly insulted that I bothered to tell you that, or you find this totally opaque. So, I don't know which, but it doesn't make any difference. We can continue. Okay. All right, so all three of these are true. Now, we also have a smiley face this time. There's a general method for determining whether a sentence in the predicate calculus based on the rationals with plus and minus, addition, subtraction, and the comparators is true. So we have a nice smiley face. And now we go to real numbers. Now, if you remember, real numbers are if you don't remember, or even if you do, I'll remind you, The real numbers are obtained by taking the rational numbers and thickening them so that there's no gaps, so that there's no subtle gaps. If you remember your classical mathematics, there's no square root of 2 in the rationals. No square root of 2 in the rationals. It's missing. It should be where it should be where it is, but it's not there. Okay, and that's an old theorem that if you have a rational number, a ratio between two whole numbers, and you square it, you'll never get 2. And this is a hardcore theorem, considered ancient. Although the ancients weren't very good at really doing real proofs. So there's a question of, if you ask who this is due to, I think you have a big historical problem. But nevertheless, we do know this. And pi is also irrational by more tricky proof and so forth. Okay, so we have real numbers in the same situation, and we have the same question. The true sentences of linear arithmetic over the reals are the same as the true sentences of linear arithmetic over the rationals. This is not at all obvious, but it's true. In other words, there's no difference between the rationals and the real numbers as far as linear arithmetic is concerned. One of the discoveries of logic. So then, nice smiley face. And so we had an algorithm for the rationals, we have an algorithm for the reals because it's the same thing. And we can even do this. Linear arithmetic over the integers, rationals, reals together. And this is useful, implemented stuff. That if there's a general method of determining whether a sentence in the predicate calculus is based on integers, rationals, reals. The same statement can have integers, rationals, and reals in it, dispersed in any way. The same statement with all this addition and subtraction and comparators. So this is much stronger than the earlier results that I was mentioning. All put together you can have them. And this works. That has been implemented. Okay. Now what happens if you also use multiplication? Well, how about with the integers, with addition, subtraction, multiplication, and comparisons? No algorithm for doing this. Kurt Gödel, 1931. No algorithm. And how about over the rationals? And remember, the new thing here is I'm putting a multiplication in. The answer is no. Julia Robinson, 1949. And now this is the surprising thing. This is very surprising. If you do it over the reals, and the reals are more sophisticated than the integers and the rationals. You know, they're a more sophisticated idea. In fact, detailed definitions of what the reals mean, you have to follow an excursion into set theory, you know, to really understand that, and so forth. So, to really understand the foundations of the real number system. So it's more sophisticated structure, but there is an algorithm over the reals for all statements with plus, times, minus, and the comparators. And that's due to Alfred Tarski, 1931 and 1948. All right, now I want to talk about another issue. What are the standards for a mathematical proof? So mathematicians are proving things, and sometimes they get into fights, fist fights even sometimes. Fights, classically in the old days, they used to be very heated fights about whether somebody's given a correct proof or not. Now, you know, in mathematics, the standards for proof are incomparably higher than they are for just about anything else we've got, you know, in the sciences or elsewhere. And so the idea is that everything is supposed to be covered. There's no possible chance for argument, and so, you know, no possible chance for disagreement. That's the ideal. So we have axioms and rules for purely logical reasoning in predicate calculus, and we also have, this is the way we set up the theory of mathematical proofs. By the way, the theory of mathematical proofs is a little different than actual mathematical proofs, as you might be familiar with the relationship between pure and applied science. It's very similar. Okay, so we're now talking about the theory of perfect mathematical proofs. So we need a unification, though, for constructing mathematical objects, because classically and historically, people just constructed mathematical objects by brute force according to whether they had enough people behind them to force it in the journals and force the stuff, to get accepted. So there was a long time in which there was no real standards for it was a little bit like every state in the United States had its own currency at one time. It's really true, and you know what kind of a mess that created. And then finally there was a unification. Of course, the U.S. dollar is not exactly the best example of a unified economic idea these days, but it certainly beats having every state have their own currency, right? So similarly here, we want some sort of federalization of the mathematics, right? So the answer is, the best answer we have today, although many people dislike this answer, the best answer we have today is what's called set theory. So the dogma is that I wear this hat. So this is a hat here. I wear this hat, that everything in mathematics is a set, and everything has to be defined completely in terms of logic and sets. So everything is a set. So this is the grand unification. And it actually works very well. It actually works surprisingly well. Now, it works so well that almost all mathematicians forget about it. In other words, they go about their own business and say, okay, set theory takes care of all of our angst, all of our problems, all of our difficulties, and now we can go ahead with the mathematics. And we don't have to worry anymore about foundations of math. So foundations of mathematics actually is a little bit of a victim of its own success, you see, in this sense. It did such a great job that people stopped worrying about it, you see. So, set theory unifies various constructions of mathematical objects. Two sets are considered identical or equal if and only if they have the same elements. So the only thing that counts in a set is what's in it. You don't care whether the set is blue, green, or purple, or whether a nice person made it up or a bad person constructed the set. You don't care. The only thing that counts is what's in it. All right, and this subject called set theory is surprisingly deep. You might think it's something this simple has to be completely vacuous, but it's not true. And it's founded by George Cantor in 1874, just a few years ago. No, more than a few years ago. All right, and Gottlob Frege formulated associated axioms in 1893 and 1903. He formulated associated axioms with a notorious axiom 5. And Bertrand Russell said, hey, Frege, called him up on the phone. No, it didn't happen that way. He said, hey, Frege, your axioms are inconsistent. I can get a contradiction from them, and therefore they're worthless. Okay, they're worthless as they stand. So he found a contradiction, and it's a very famous thing called Russell's paradox. You can look that up. And I've seen two different dates on it. I guess it depends on the date of the actual letters and maybe the time of the phone call or whatever it was. So the 1903, I've seen dates on it. Okay, but Russell fixed this. Russell says, and furthermore, I know how to fix your axioms to make them okay. And this was called the theory of types. And it has implications already, even today, with the computer scientists doing type checking in their programming language methodology. It has an influence even to this day. But it was completely supplanted by formalized set theory at the time. And formalized set theory, which I'm not going to go through these actions, don't worry. I just want to give you an idea that there really are such things. And Ernst Zermelo in 1908 made a big breakthrough, replaced Russell's type theory by this much simpler system, which is much more basic, much more friendly, called Zermelo set theory, named after Zermelo, 1908. And these are very specific axioms. And then Zermelo set theory easily suffices to develop the main basic infrastructure of mathematics: natural numbers, integers, rationals, reals, complexes, addition, subtraction, multiplication, division, ordered pairs, and so forth. And mathematicians sit on top of this, taking it for granted. And it was extended by Frankel to Zermelo-Frankel set theory with the axiom of choice. There are some missing things in Zermelo's set theory that are not necessarily fatal, but it's important. But it turns out to be a very good idea to round out Zermelo's set theory a bit with a couple of additional principles. But the story would take us too far afield. So then we have what's called ZFC. ZFC is the gold standard. We're actually off the gold standard, aren't we? But we're not off the gold standard in mathematics. We have a gold standard in mathematics. There is an absolute arbiter as to whether or not a proof is actually completely correct. That is, can it be formalized, or is it formalized in the ZFC axiom system is the gold standard. And of course, the gold standard is never actually used. It's sitting in the background in case there's going to be a fight. And we don't usually have, we don't usually have fights that are relevant to ZFC. But it has a very useful purpose of this gold standard, unused gold standard. Okay. Now, why do we believe in ZFC? So here we have all these axioms. We have the rules of the game, the rule book for mathematics. Why do we believe this rule book is reasonable? Now, what do I mean by reasonable here? Why do we believe in this rule book? Meaning, for example, how do I know that this rule book doesn't allow you to get an inconsistency? That is, prove something and its opposite. Maybe this rule book allows you to prove 2 plus 2 is 5. And everybody knows how to prove 2 plus 2 is 4. So we have a real problem because 5 is not 4. How do we know this? So this became a burning issue. Fine, we got rid of the mistake that Frege made in his famous axiom 5. We got rid of that. Russell got rid of that and said, here's what you should be doing. And then Zermelo said, this is what you should really, really be doing. And then Frankel said, let's round it out. So we got this ZFC system. How do we know that we can't Fregeise this? Maybe there's something as bad as what Frege did in this ZFC. So this became a burning issue. Well, I'm not sure that I'm giving you the real story in the right order because I'm jumping to something very modern here. In fact, maybe I should. Okay, the basic idea. Okay, let me jump to the modern thing. All axioms except the infinity axiom, that there's an infinite set, are easily seen to hold in the world of finite sets. The problem is the infinite world. The world of infinite sets is the possible issue that could cause a problem. And it has been shown that our axioms of set theory arise from transferring the simple principles that obviously hold in the finite world to the infinite world and adding the axiom of infinity. So we know in some sense now that our axioms for infinitistic, full-blown infinitistic set theory, ZFC, are essentially the lifting and extension of the axioms in the finite mathematical world to the infinite. So this may tend to give you some confidence that these axioms are okay. But it's not the final story. The final story is actually earlier. Okay, and enter Kurt Gödel with 2 blockbuster results. Okay, the first result responds to the first issue. Is ZFC, the gold standard rule book, enough to settle? Is this rule book enough to prove or refute all statements in mathematics? In other words, if I have a question in mathematics, can I go to the rule book and say, I can either use the rule book to prove it, or I can use the rule book to refute it? In other words, is the rule book complete? And Gödel showed that it is not complete. Gödel showed that the rule book is not complete. There are always sentences that, in fact, even in integer arithmetic with multiplication, there are sentences that cannot be proved or refuted using the rulebook. Furthermore, Gödel showed that no rulebook is complete. No rulebook is complete whatsoever if the rulebook can be described as a rulebook. I mean, you could really write down the finite number of rules involved. No rulebook can be complete. So this is a very important result, first incomplete story. Now, but what about the issue of whether our rulebook is consistent, doesn't have a contradiction, which is what I was talking about earlier. What about that? That's a little bit of a different issue. The second incompleteness theorem of Gödel says that ZFC itself is not sufficiently strong to prove that the axioms of ZFC are okay. In other words, what we have is the following result, according to Gödel. The rulebook is not enough to prove that the rulebook is okay. That's what Gödel proved. Gödel proved mathematically that the rulebook is not strong enough to prove that the rulebook is okay. Furthermore, he has a more general result that no reasonable rulebook is enough to prove that it is okay. So this deserves a 2 frowns, actually. Actually, maybe infinitely many frowns. Okay, infinitely many frowns. This is a very, very bad thing. In fact, the affectionate name that logicians use for this is called Gödel's curse. Okay, this is often called Gödel's curse. This is how bad this is. Okay. All right. Now I'm going to change the subject. That's the end of the pure, foundations of mathematics part, and we're now going to talk about other interdisciplinary aspects of logic. Now, large programs are expensive and buggy, and there are many reasons for that. We need a major overhaul in programming environments to deal with this, and logic will play a central role. How do I know that? Well, I can see my crystal ball says that it will play. No, I think I have some reasons to believe this. Now, here's some software disasters just to give you an idea of how dangerous this world is. Therac 25, a radiation therapy machine involved in 6 accidents, 85 to 87. Patients given 100 times intended dose. Factors include bad software design and development. Not that there's a bunch of poison in the stuff. I mean, not deliberate poison or something. It's a software problem. Okay, now, Ariane 5, a launcher for rockets, blew up in June 1996 from a failure of the inertial reference systems traced back to a piece of software. The Intel Pentium bug. Intel's Pentium computer chip was recalled in '94 at a cost of $500 million US, which is still a significant amount of money, even though the dollar it may not be a significant amount of money for the foreseeable future, but it was back then. All right. So the floating point arithmetic software was flawed. All right. One thing we need is formal specifications. Formal specifications. In other words, somebody builds a piece of software. There's a notion of what is it supposed to do. Now, what is it supposed to do shouldn't mean that a bunch of people working for the company that build it, sit down in front of it in a table and talk it out about what they want it to do, and then they leave the company for higher salaries elsewhere. And then what have you got? Okay, so that's the extreme case, right? So formal specification is supposed to be an exact description using logical language, an exact description of what the software is supposed to do. And that's not an easy thing to do, and it's also generally believed to be too hard to do, but not in the future and not in certain situations. And there has been progress in all these things. It's just not, the progress is not strong enough to completely change the culture. So, so this is not, this is certainly not complete fiction. It's just very difficult and very expensive to do this kind of thing. All right. It will be written in applied predicate calculus, and it's needed to support reusability of software so that when people leave a company, you've got something left that you can modify. You don't have to start all over. And the verification of software, which is the great dream of all this, that you can actually know that software is correct, not simply by testing cases and then all of a sudden the software blows up on you on some case you never thought of. You want to avoid that. You see, you need techniques from logic for this. So, what is software verification? I mean, you want to have a mathematical proof that the software obeys the formal specification, and this is far beyond the usual software testing and common practice in industry, and we want a programming environment where a team of software developers writes code and verifies the code. And there are groups in the big computer companies, on an experimental, very limited basis, doing this kind of thing. I mean, it's not a total pie in the sky. It's just it's not a common thing for very large systems at this point. Programming languages need an overhaul. Heavy-duty tools need development. Tools include algorithms from logic refined by computer scientists, as discussed previously. And the work is highly exploratory. Not clear how to design a working system for cost-effectively creating verified code for real-world programming situations, but this will evolve. Now, there are potential applications of logic in education. I think some of them are really exciting. You want to develop systems that automatically generate multi-step homework and exam problems, satisfying instructor-controlled parameters. So you can see this as a logic issue. You're going to have one kind of program that any user, you don't know what the students are going to get stuck on, and what they're going to get stuck on after you help them with those errors, and so forth and so on. So you have this gigantic tree, which is too big to list all the possibilities as to what can happen in the interaction. And you also have to define the interactions carefully. So the whole thing is really an extreme case of logic, mathematical logic, if you look at it this way. And we really don't. I mean, we're just beginning to understand this. The demand for it is starting to get serious with these large course initiatives all through the world. With the idea that it may be cheaper to teach 10,000 students at once than 10. I mean, it's an idea that could have some merit in it. I don't know. But the point is, if you're going to teach 10,000 students absolutely nothing as opposed to 10 students a lot, then maybe the second might be better than the first, right? So the idea would be to teach 10,000 students a tremendous amount each, right? It would be the ideal, right? So we want to get to that point. All right. So automatically graded, student enters multi-step solution in specified format, obtains feedback after each step. Full history of student responses on all problems stored to adjust and used to adjust further future problems. So, in other words, according to what the students are doing, they get different problems, generated different problems according to their strengths and weaknesses from what you can tell with the interaction. It's a big logic issue. Everything has to be pinned down. The meaning of all the interactions have to be specified, and so forth. Data used to fine-tune instructors' lectures. Okay, so you have all this data, in real time. I mean, this is the university of the future, perhaps. Okay. Now, the ideas, of course, have been around, and the challenges make automatically generated multi-step problems truly reflect course goals, and the interaction engage the students appropriately. You need sophisticated problem templating, reflecting many degrees of difficulty, needs formal structure to support real-time computer grading, need formally structured. Computer grading is quite easy if it's a multiple choice thing, but it's much more difficult when you want to talk about much more delicate tasks. Need formally structured modes through which students enter multi-step solutions and receive feedback in real time. Okay, the logic needed everywhere. Now, I already started a project like this, very embryonic, with a limited amount of resources, and I don't have time to actually tell you much about it, but the future targets are epsilon delta proofs in calculus, which have been abandoned largely because in the United States for average students, and even well above average students. Even at Harvard University, they stopped this except for math majors. Okay, now I say this is more to do with the lack of imagination, imaginative technology in the teaching than it is any reality with students. That's the thesis. You can argue that this is not the case, but I strongly believe this. In other words, you can take a cat and teach them epsilon delta. No, not a cat. It has to be higher intelligence than that, but you can actually push the boundary quite a bit. All right, epsilon delta proofs in calculus, courses in the mathematical sciences, and courses in engineering and beyond. And now I want to talk to you for a few minutes about theology. Now, I'm not going to tell you what my theological attitudes are because it's totally irrelevant. I'm a logician, okay? And this is a topic for me to do some logic on, okay? So if you're, what you believe in and what you don't, you can still listen to this independently of what you believe, okay? Now, there have been many attempts to prove the existence of God using the concept of positive properties. Positive properties, these are the properties that are good to have, and if you don't have them, you're flawed. And nobody's perfect except God. That's the idea behind this idea. Most notably, Leibniz, co-inventor with Newton of the calculus, and Gödel, the great logician we've encountered before. These attempts go under the name of, there's a thing called the ontological argument for the existence of God, and they're extremely controversial. We use the concept, now, I don't want to get into that, and that's not what I did here. But we want to use the concept of positive properties for quite a different purpose, a totally different purpose. Leibniz, Gödel, they wanted to use the concept of positive property in connection with properties of God and proofs of existence of God and so forth. Okay, and that's not what I'm trying to do. Instead, I want to use the concept of positive properties. This is an abstract, ephemeral concept. We want to use the concept of positive properties to prove that the usual ZFC axes for mathematics are okay. That's what we want to do. So remember, Gödel showed us, I want to show that the rule book for mathematics is internally consistent, i.e. in some sense okay. And I want to prove this using positive properties. I want to prove this. And remember, Gödel said that the rule book itself is not sufficient to show the rule book is okay. So Gödel said that you have to go beyond that rule book to show the rule book is okay. And I'm going beyond it if I use positive properties, because I haven't found in the rule book anything about positive properties. This is part of theology, not part of mathematics. So I want to use theology to prove that mathematics is okay. In other words, a concept from classical theology is used to prove that mathematics is free from contradiction. So I go on a while for this, and I may cut it short a little bit, but I'll go through it quickly. In this framework, we consider properties and attributes of properties or attributes of things. Here are three interesting examples. Possessing an intellect, knowing at least as much as any other thing, knowing more than any other thing. Those are three abstract, interesting attributes. Now, certainly these properties are positive in the sense that it's better to have them than to not have them, right? But there is the question of whether these properties are possible to have in the first place, and the first one obviously is possible. I don't know about me, but somebody in this room thinks they probably do have an intellect, right? So possessing an intellect is possible. All right, and the second and third are, of course, more problematic. Now, here's some general principles. For any given property, it's either positive to possess it or it's positive to not possess it. And if it's positive to possess P and it's positive to possess Q, then it's positive to possess both at once. And a perfect being possesses all the positive properties. There is a perfect being, and there's exactly one perfect being. All this stuff can be sort of analyzed mathematically and all that stuff. Okay, so those are some general principles. And now let's return to these examples. Possessing an intellect, knowing at least as much as any other thing, knowing more than any other thing. To apply the general principles, we need to know that it's possible for a being to have these properties, but the first one is not problematic. We can argue for the second. For any given x, it's positive to know at least as much as x. It's positive to know at least as much as x. I mean, x knows at least as much as x, and it's positive to know at least as much as x, and negative not to. So that means that a perfect being knows as much as any other thing. Any other thing, because x is now can be anything. So you can play around with this and get that you can reason that a perfect being knows, you can do this informal philosophical discussion and get that a perfect being knows as much as any other thing. But there is the question of whether a perfect being knows more than any other thing. And then you get into deeper territory, which I've never worked on. But probably you could probably do some general logical principles to show that a perfect being knows strictly more than anything. Probably you can do this, but but I haven't worked on this. Just want to give this as an example of an indication of how one can at least attempt to intelligibly navigate such murky waters. In other words, you can put on your theological hat and do some science. That's what I'm saying. All right, the supernatural and the natural. So the perfect being is clearly part of the supernatural world and not part of the natural world. In the natural world, beings have a lot of positive properties, but not all of them. You've heard the phrase, nothing is perfect. Nothing in this world is perfect. Nothing in the real world is perfect. We expect that for every natural being, there is another natural being which possesses all of the positive properties of the first and more. That seems very likely. In other words, that given anything, there's something better. In the real world. Now, in the supernatural world, there's God, there's nothing better. Okay? And I turned this into a piece of science. We start with the universe of natural objects as opposed to supernatural objects. We use the concept of properties of objects that's used in mathematics. We use the theologically based concept of positive properties of objects, and we assume the general principles I've discussed, which correspond in mathematics to those mathematicians here of what's called a non-principal ultrafilter. Now, if the phrase non-principal ultrafilter means nothing to you, that's just fine. Okay? All right. We do not have a natural object that possesses all positive properties. That's only reserved for God. Now, an angel is an object which possesses all definable positive properties. In other words, any positive property you can name explicitly. Not just any abstract positive property. Any positive property you can name, an angel must possess. That's my definition of an angel. Okay? That it obeys all the positive properties that at least you can name. And that's pretty good. That's pretty good. I mean, God is better, right? It satisfies all positive properties, but it's not part of the real world. But an angel might be part of the real world. There's an issue, right? Okay. Now, the axiom is that there exists an angel. That's the axiom. The key axiom in this science is that there exists an angel. That is, there is an object in the real world which possesses all explicitly definable positive properties. And we've been able to prove using an angel, or using the existence of an angel. I personally don't know any angels, except my wife in the first row. That's the only one I know. That mathematics is free of contradiction. In other words, I can prove that the rule book is okay if I have an angel. Whether I should thank the angel for this is another issue, but I'm just saying that the existence of an angel is very powerful. And I hope you found these interdisciplinary adventures, which are varied, of some interest. Thank you very much.
Yeah, dear Professor Friedman, thank you very much for this very interesting talk. The official program will start at 5 o'clock. Now we have still 50 minutes, and I think there is time for questions. So if somebody wants to pose a question, it's maybe now a good moment for this. Yeah? Yeah? Who wants to pose a question? Well.
Okay, so I'm from Oslo, and my question is related to the more theological things, because I also did some work actually on this good ontological truth. From what I remember, there are two important papers more in the philosophical tradition. One by C. Anthony Anderson, which showed that Gödel's modal apparatus leads to modal collapse.
Yeah.
So that the assumptions that Gödel made in his notes, handwritten notes from 1970, led to the conclusion that all statements are necessarily true. And these matters were rectified then by C. Anthony Anderson. I was wondering, in a paper that was a response to so the first guy was Gödel Sombel of Toronto that showed that there's collapse. So I was wondering if you said that as taking these matters into account.
Yes and no. They don't take into account because they don't need to be taken into account. Let me explain. I use only the tiniest part of Gödel's apparatus. I stay 1 million miles away from modal logic. I just use something that actually goes back to Leibniz, which is basically that there's a thing called positive properties that forms an ultrafilter. I'm using essentially none of the, I'm not using any of the commonly cited controversial aspects of Gödel's approach. That's why I said I was not but Gödel needs that kind of stuff in order to argue that God necessarily exists, and I'm not doing that at all. Now, I hesitate to say that I'm not using anything controversial, because the very idea that there's a thing called positive properties is a deep, theologically based idea. Just the very idea. But the only thing that I'm using is just the very idea of it, and I'm not using, and I'm staying 1 million miles away from anything connected with modal logic or the ontological argument.
Okay, thank you very much. Now the other question?
This framework, are you able to specify the exact set theory that you can buy from the theological perspective?
Yeah, there's a paper just accepted for publication, modulo trivial editorial comments for Notre Dame Journal of Formal Logic, which is on my website, called A Divine Consistency Proof for Mathematics. And what I do there is show that it is trapped between, are you a set theorist at all? Okay. It's trapped between the existence of arbitrarily large Ramsey cardinals with a stationary homogeneous set, formulated with a stationary homogeneous set, and a measurable cardinal, strictly in between. And only a set theorist would be doing this. Everybody else would be doing what? You know, so I know you are a set theorist.
Okay, thank you very much. I would suggest now to stop the session with questions. Let's thank the speaker again.